So, now let us see the emission characteristic of surfaces. So, first we will take a black surface. So, black surface. So, a black surface means the surface of a black body, anything we can write. So, black surface means the surface of a black body. So, what is a black body? So, in physics, black body is an ideal object as far as thermal radiation is concerned, which is capable of emitting all wavelengths as well as it is capable of absorbing all wavelengths. So, now let us see a black body or a black surface. A black body is capable of absorbing all radiations of all wavelength falling on it. So, whatever falls, it will absorb all the radiation and of all wavelengths falling on it. Since it absorbs all radiations without reflecting and transmitting, so its color appears to be black. That is why we say black surface. Even a light of different color which is incident on it, since absorbed. So, even a light of different color which is incident on it, since absorbed, so does not show its color effect. That means, if we shine a red light on a black body, then the body will not appear red, but still the body will appear black. This is why a black body has a black color. So, one very important point is that we call a black body only when it can absorb all radiations of all wavelengths falling on it. So, this is the reason why we call it a black body. It is not so because of its black color. So, thus a black body may have a black color, but a black colored body may not be a black body. So, this is an important point. A black body may have a black color, but a black colored body may not be a black body. So, very important point. So, the last, let us summarize this point, that a black body may not be a black colored body. So, black body is not just a black colored body. So, that this is different, black colored body is different, black body is different. So, black body may have black color, but a black colored body may not be a black body. So, black colored body is different thing and a black body is different thing. So, this is something related with the color of the black, but this is related, black body means, I say it means that it can absorb all radiation irrespective of wavelength. This is black colored body. In lab, this is an ideal body. So, in lab we make a black body, that is called Fairy's black body, in which we take a copper sphere and make a pinhole in it. Let us see how we do it. Now, black surface, black body, Fairy designed a model which very closely approximates a black body. That is, the properties of this model is very close to a black body. So, what is the idea? A spherical copper shell was taken. The inner surface is blackened and a pinhole was made by Fairy. So, what he did, he took a hollow copper shell and then he blackened the inner wall. So, this is blackened. So, I am just shading to tell that actually it was blackened. So, the copper, and you see a pinhole was there, a very small hole, we call it a pinhole. So, light can be incident inside this through this hole. So, now any light incident through the pinhole is completely absorbed by the blackened surface of the spherical shell. Now, suppose a light directly comes, so very opposite to it a conical ridge was made, so that if a light directly falls, it will be reflected here. A conical ridge was made just opposite to the pinhole, so that any unabsorbed radiation of any wavelength will be reflected in other direction and will be absorbed by multiple reflections. So, you see, suppose this ray goes, if it is absorbed, okay, otherwise it will be reflected and then some part will be absorbed like this. So, finally it will be decaying like that. So, the radiation will be absorbed. Thus, a very small fraction of radiation will come out once it enters the Fairy's black body. So, this was approximated as a black body. Now, suppose I want to see how a black body radiate. Now, in order to study the black body radiation, if we want to study the radiation emitted by a black body, then we heat the Fairy's shell and the whole radiates very nearly like a black body. Thus, this is an approximation of a black body. Now, let us see the total emissive power of a surface or a body. So, total emissive power of a body is the amount of energy radiated per unit area per unit time by the body. In other words, it is the radiant flux. So, this is the amount of energy radiated is called radiant flux per unit area by the surface. So, radiant flux means the total amount of energy passing per unit time. So, this is what we define total emissive power. Its SI unit is watt per meter square, and or in short we write as watt per meter square. So, the symbol we denote it by E. So, for total emissive power we use the letter E. If it is a black body, the total emissive power of a black body is denoted by EB. So, we will use EB to denote the total emissive power of a black body. Now, we will see what is the total emissivity. Now, let us see what is total emissivity. So, you see, first of all, let us see that the total radiation emitted by a black body is always greater than that of a similar real body. So, a black body radiates more energy than a similar similar real body or non-black body at that temperature. Thus, a black body is a benchmark in emitting radiation at any wavelength for the same temperature. That means, in order to define the total emissivity of a real object, I have to compare it with a black body. That is the emissivity of a black body. So, therefore, we have to define the emissivity. So, thus total emissivity of a real body is the ratio of total energy radiated per unit time per unit area to the total energy radiated by a similar black body under similar conditions. Conditions means here temperature. So, thus this is a ratio and it is denoted by epsilon, that is E by EB. That is the total emissive power of a real body. This is the total emissive power of a real body to the total emissive power of a identical black body at same temperature. This is what we define epsilon. Now, you see this EB is always, the black body will always emit more than this. So, we will have the range of epsilon as epsilon will be greater equal to 0 and less equal to 1. So, thus we define the total emissivity as the ratio of the total radiated power, that is radiant flux, by the radiant flux of a black body. Now, let us see what is monochromatic or spectral emissive power. Now, certain bodies may not radiate very well in all the wavelengths. So, they radiate more in few wavelengths and less in other wavelengths. So, in order to define their emissive power, we use their monochromatic spectral emissive power. So, we define monochromatic or spectral emissive power as the radiant flux, that is energy per unit time, radiant flux per unit wavelength, per unit area We define monochromatic or spectral emissive power as the radiant flux per unit wavelength per unit area emitted by a real body. So, we define this, its symbol is E lambda. So, you can see this E lambda is the symbol and E lambda is total energy, delta U energy radiated per unit time, that is delta T, and this is per unit lambda, that is delta lambda, and then it is per unit area, so delta E. This is this E lambda. It is in watt per meter square lambda. Now, the total emissive power will be given by the integral of monochromatic emissive power over lambda, that is E will be written as E lambda into D lambda. Now, if we plot a graph of lambda and E lambda here, then we get a graph like this. So, total radiation emitted, total energy is the area under this curve. Total energy is area under this curve. So, is equal to the area under the curve of E lambda versus lambda, that is monochromatic emissive power versus lambda. Now, if it is a black body, then we denote that the total, the monochromatic emissive power of a black body is denoted by E B lambda. So, we use this term for a black body. Now, let us see monochromatic or spectral emissivity. Now, you see, a real body will always emit lesser than a black body, because a black body is the benchmark in radiation for any wavelength. So, what may happen that the real body for certain wavelengths will be very close to the black body, but for other wavelengths it will depart very large from the black body behavior. So, that is why in order to compare its closeness to a black body, we require the monochromatic or spectral emissivity. So, it is the ratio of monochromatic emissive power of a real body to the monochromatic emissive power of a similar black body at the same wavelength and temperature. So, we see we have epsilon lambda is equal to E at lambda and EB at lambda. So, this is how we define this ratio. Now, let us see in graph what it will be. So, let us plot E lambda as well as EB lambda, and here lambda for E lambda for a real body, EB lambda for a black body. So, this is the plot of monochromatic emissive power. This is for a black body. So, this is for a black body. Now, a similar emissive power, monochromatic emissive power for a real body will be a graph somewhat like this. So, it will be slightly less than this. So, let us see what will be this term. So, what we do, we take a particular value of lambda, suppose I say lambda 1 or lambda naught, and then we go like this. So, this is A, point A, this point is B, and suppose this point is C. So, thus in the graph E lambda naught means this is the value of lambda naught. So, I write the emissivity at lambda naught, monochromatic emissivity at lambda naught will be the ratio of E lambda. Now, this is E lambda here AB by this AC. So, E lambda, that means for this real object, this is real body. So, for real body, AB is the monochromatic emissive power, that is AB, and this AC. So, this ratio will be the ratio of how much it departs from the black body behavior. So, you see why I choose this. Sometimes the graph may not be very similar to this. So, for some bodies this black body graph is like this. So, this is the graph of a black body, this is the black body, and this graph is here something like this for a real body. So, you see for these values this range of lambdas, this real body is very close to a black body, but beyond this graph departs very away from the black body. So, this is real body and this is black body. So, we will not get an estimate of how much a real body departs from a black body just by seeing the total emissivity. Now, what will be the total emissivity if in order to define total emissivity, this is lambda and this is our, for a black body this is the graph. So, the area, suppose I say this area has area of 1 and the area under this curve is A1, and this is for a black body, this is for a black body, and the similar graph I have drawn, this is for a real body, and this area is A2 and this total area is A1. So, you see the E, that is the emissivity, which I call total emissivity, that was the ratio of this area, this A2 by A1. So, this total area under this curve The ratio of the total area under this curve of a real body to a black body is the total emissivity, and the ratio of the ordinates will be the monochromatic emissivity. Now, let us see what is a grey surface. So, a grey surface is a concept similar to black body, that means it is just an ideal assumption. So, just like a black body, it is an ideal assumption. So, a grey body, a grey surface is a surface which has the same monochromatic emissivity, that is E lambda epsilon lambda at all wavelengths. So, let us plot a graph to understand the behavior of a grey body. So, you see this is lambda that varies here, and we have here emissivity, monochromatic emissivity. For a black body, this is E B lambda, that has a value of 1. So, this is value of 1 for a black body. So, black body has emissivity 1 and it has the same value at all wavelengths. But for a real body, the monochromatic emissivity is not constant at all wavelengths and it will vary like this. So, it will be different for a different real body. So, for a grey object, it has a constant value at all wavelength. So, you see this is the emissivity for a real object, real body, and this graph is for a grey body. So, a grey body will have this type of graph. So, now let us see if I plot. So, this is what is there. Now, let us plot this in lambda versus E lambda graph. Now, let us see what does it mean. Here we have plotted lambda and this is E lambda, the emissivity, emissive power, monochromatic emissive power, and we got this graph for a black body. So, this is the graph for a black body. So, emissive power, that is spectral emissive power of a black body, variation of spectral emissive power of a black body. So, you see for a real body, this graph may be like this, and you see it may be something like this. So, you see if you take this emissivity value, this ratio by this, that is epsilon lambda, that is E lambda by E B lambda, then you see this may not be the same, this ratio will be same for different values. So, this is the for a spectral emissive power of a real body. If I have to draw such a graph for a grey body, then that graph will be very smooth, such that the ratio this by the total is maintained throughout this. This is what I have used here this E emissivity and lambda graph, this is for a black body that is equal to 1, and this is for a real body which will be changing, and for a grey body that will be same. So, thus a grey body, a grey surface has the same value of monochromatic emissivity at all wavelengths. This is an ideal assumption for simple calculations.